So welcome all. This is week 12 tutorial for the course Deep Learning. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. So we're gonna cover, this is the last week of tutorial for this course. So today what I plan to cover is based on the week 12 content of the course. Just a second. Yeah. So topics that I plan to cover today are Encoder-Decoder Module, and then we are also going to talk about a variant of attention mechanism. So the attention mechanism that we would be covering over here is similar to what is covered in the course. Uh, these days there are a lot of new attention mechanism after which this transformers and these kind of things are motivated. So you can also like have a look at those kind of attention mechanism like later on after this course or somewhere. So this is one thing. Okay. So till now in this course, the things that we have done includes our normal feed-forward neural network. Then we did CNNs, we did autoencoders, and then we did this language-based models that were RNN, LSTM, or GRUs, right? So if you recall, what we did in autoencoder was if we had some input data, right? We tried to suppress it to some lower dimension and then regenerate the original data using this lower dimension representation of data, right? So over there, our loss function, if this is x, this is x tilde, loss function looked something like x minus x tilde, right? So the motivation for, so we call this left part as encoder and the right part as decoder in case of autoencoders, right? Now the motivation for encoder-decoder module is also same, that we want to do something similar, but now what is the difference from autoencoders is so if you have some input, you are going to some representation, and again then you have some output. Okay, so now the kind of architecture that you are using for encoder need not be same as the kind of architecture that you are using for decoder. Okay, also we don't want to regenerate the input as it is, but we want to generate some variants of input. For example, if you want to do language translation, so I want to convert a sentence in English to a sentence in Hindi. So what I want to do is that I want to input the sentence in English and I should get an output that is a sentence in Hindi. So I'm looking for an appropriate sort of representation or encoder and a decoder module, so that if I use that, I'm able to do this kind of translation. Okay, now we have sort of almost covered all types of networks that are useful. So you have simple feed-forward neural network that you can use on IID data sets. For example, if you have RN kind of data set, you have CNNs that you can use on images. You have these kind of things that you can use on sequence data, specifically language. Okay, so we can motivate lot of application, lot of tasks from these sort of combination. So we'll look what encoder and decoder module is. Okay. So here is one example that we can try to solve using this encoder-decoder module kind of thing. So let's say we have an image, we want to caption this image. Okay, so the task over here is of image captioning. Okay, so now so what is the input that we have? Uh, Input we have is an image, right? We want to convert this image to some suitable representation or some. So you might hear these words in different contexts. First is representation. Second is encoding. Third is embedding. Okay, these are loosely speaking sort of same. Okay, so these are sort of similar terminologies used for some. So you might also hear something like latent representation. Okay, so latent means hidden. You are not explicitly finding the representation, but in the process you are sort of doing this. Okay, so right now what we have image as an input. We modify this image to some form that we can pass to something that, so okay, so we have what we have as an output. We have a sentence as an output, right? So if you want to process image, what is the best option that we have? We can use something like CNN. And if you want to process sentences, what option we have? We have RNNs or LSTM or GRUs. You can use any three of these, but right now I'm using RNN just for the discussion purpose. You can use any of these. Okay, so what I want to do is, from the image I want to sort of store all the information in a form so that I can pass that to this RNN. Okay, so I want to convert this to a vector. Okay, and then I pass it on to RNN so that RNN can process information out of this vector and generate the caption for this. Okay, so this is the overall idea. And if you look at kind of network that we had in autoencoders, so in autoencoders, both encoder as well as the decoder were trained at only at one time instance. What do I mean by that is, so we didn't train the encoder separately, we didn't train the decoder separately, but based on this loss function, the weights of encoder as well as the decoder were being updated. Okay, so similar thing would happen over here also. So you don't explicitly train the CNN, you don't explicitly train the RNN, but you create a sort of a complete network, and based on the loss of this RNN, the weights of CNN will also get updated. So what does that actually mean is that uh, based on the kind of captions that you want, the kind of caption that you have in your data set, the weight of your CNN and hence the representation that you are having will also get updated. So just a small comment over here is, let's say from image, you are trying to do two kinds of tasks. First is you want to identify if you have a person in the image, if you have a human being in the image. Okay, and second task is, like, let's say you want to, similar to this, you want to generate caption. So what I'm trying to say, this is very trivial, but I just want to mention it, is that let's say if you are training an encoder-decoder kind of module, then the CNN that you would obtain in this case, let's say this is CNN1 and this is CNN2. Although what I said is, using CNN, what we are trying is, we are trying to store some information in form of a vector, but the CNN that you will obtain in case of the first task and the CNN that you will obtain in case of the second task need not be same. Actually, they won't be same, like if you look carefully. Okay, what do I mean by CNNs not being the same? The weights that they will learn will be different, and hence the representation, the intermediate representation that they would be learning would also be different. Okay, so let's look at one of the examples. How does this thing work? So let's say this is your image captioning task. Okay, so what you will do is, you will begin with your image, you will pass it through a CNN, then using whatever extraction the CNN can do, then you will sort of create a fully connected layer towards the end, and you will get this vector H0. Okay, this H0, the output that you have got, you will pass this as the S node for your RNN. So you remember you had an S node in the RNN. So you can pass this S node as your, so this is, there are two options to do this. This is usually called option 1 in your lectures. So you'll pass this as an S node to your RNN, and then your RNN will generate sort of a sentence for you. Okay. So let's say this was your input. Okay. So what is your sort of H node? H node is CNN of, why is it written CCN? H node is CNN of X node. Okay. And then what is happening at the generation process? So what will happen is, let's say this is your ST. What is ST? ST is RNN of, now what are the inputs that you have to ST? First thing that you will have is ST minus 1 that you would get through this weight connection, right? And then what would be the input to this? What would be the input to this thing? The input to this thing would be the previous output, because you want to sort of look at the next word when you are generating a sentence. So people represent this by y of t minus e of by t. Okay. So this is sort of your the what will happen in this encoder decoder kind of module. So this is sort of your encoder part. This is your decoder part, and the loss function and those kind of things. So what would be the loss function? Loss function would be similar to RNN. Okay. And again, the training would be done via gradient descent. So when you apply gradient descent, let's say at this level, it updates weights all the way up to this weights of this CNN. Okay. One more small thing is that your model, like whenever you're training an RNN, your model should also learn to sort of generate this stop, right? So you should know when to stop and sort of that when you have started. So when the sentence finishes, your model should tell you explicitly that you have finished the sentence. So you should not keep an count of like how many times you need to sort of run this thing. Your model should tell you when to stop. Okay. Okay. So this was the option 1. Now, if you sort of look at this option 1, one problem that this option 1 can have, let's say you want to generate a long captions. Okay. So because the information is flowing through this channel, it is going from here to here. If the sentence is pretty long, then this initial information that we are feeding in might get lost, let's say after 10 or 12 sort of like this are time steps. Okay. So one option to overcome that is, rather than just inputting this H node that you obtain from the image to the first time step, you can input it to all the time steps. So this might solve that purpose, that in generating long sentences, so yeah, the information will not get lost. Okay, these are just the two options that we have mentioned. Again, you can have numerous options. One option is that you sort of input it to even numbers, right? So you input here, you input here, you input here, skipping one connection. Because if you look at this, if you have passed information over here, then it is okay to expect that the information will flow at least to the next time step. And it has started dying over here, so we are again inputting it. So you can do a skip connection of 3, skip of 2, those kind of variants you can definitely try. Okay, so these are other options that you can look at. Okay, so for this image capturing task, you inputted your image to a CNN, then got a representation out of CNN. You input that representation along with the other things to your RNN to generate the caption for that particular image. Okay, the loss function is similar to that of RNN, and like the learning algorithm is again the gradient descent. You will do gradient descent to learn your parameters. Okay, any doubt till this point, or any clarification or anything you wanted to ask? So now I have included some other applications of encoder-decoder module. What are the tasks you can perform using them? You can perform a lot many tasks other than what I have mentioned over here. But one is image captioning that we just saw. Okay. Another thing is machine translation. Okay. So this is your machine translation, how your machine translation network would look. Now, in the previous example, you had image as your input. Okay. Here, what is your input? Input is also a sentence. So how do we process sentences? We process it via RNN. Okay. So here is an RNN module. So you process your I am going home via an RNN, and whatever is the output of your last time step, you pass it as an input to your first time step of your second RNN module. So this is RNN1. This is RNN2. So weights over here would be different from weights over here. So this would be U2, this would be U1. So these are two different RNN modules over here. Okay. And this way you can sort of, again, there would be also a stop kind of thing that you should have. Okay. So there would be a one more arrow over here where you input and you should get stop. Okay. So again, here your input is sentence. That's why you processed it via RNN. And your output is also in sentence. That's why you have an RNN module over here. So this is the representation that I was talking about initially. This is the representation that you're passing to your second decoder module. So this is your encoder. This is the representation, intermediate representation, and this is your decoder. Now, how would your loss function look over here? Because your decoder module is an RNN, so loss function will be again your sum of cross entropy, which is your usual loss for RNN. Right. Again, the learning would be via gradient descent. And the parameters of this RNN as well as this RNN will be learned in one go when you're optimizing the loss of your RNN2. Okay. Okay. So again, the second option similar to what we discussed in case of image captioning. So here also you can have this. This is the representation that you had. Okay, let me change this thing. Yeah, this is the representation that you had. So rather than just inputting it to the first time step of your second RNN, you can input it to every time step along with this E of IT minus 1 and S of T. Okay, so now your RNN2 will have three inputs. The first one is your S of T minus 1, and second one is the concatenated E of Y T minus 1, comma, this is H of T, let's say, H of capital T, let's say. Okay, so this is the input to your RNN. Okay, another task is image question answering. So in this task, what is the input that you have? In input, you are given with an image, and second is a question based on that image. Okay, so for example, in this case, you have a figure, and the question is, what is the color of the bird? Okay, so how can you sort of do this kind of things? So you don't have a architecture right now, at least in this course, that can handle image as well as words, right? You haven't learned architecture that can handle image as well as words. People have proposed all sort of things. So you can, in literature, you can find a model that can sort of work for both kind of these things. But at least what we have done in this course, we don't have a model that can tackle both of these things. Okay, so what we will do is, we will pass the image via CNN. Okay, so we'll pass the image via CNN, and we will pass the sentence or the question via RNN. So let's say using the image you obtain this h of t, okay, and using this RNN you obtained h of I. Now what we will do is we will concatenate both of these. Okay, so we will have h of t and h of I, and we will pass this to our decoder module. Okay. Now in this case, what is our decoder module? So we have to guess the color of, so not guess, we have to tell the color of this image, right? So this is sort of a classification task. So what is the kind of architecture that we learned for simple classification? It was a feed forward neural network, right? So this block over here represents your feed forward neural network. So this concatenated vector will be the input, then you will have, so let's say this is your input, then you will have some layers of this, and at the end you will have this softmax kind of thing that will tell you the probability of different colors. Okay, so what is the loss function that we use for this kind of network? Loss function would be again cross entropy. Now this is not sum of cross entropy, this is just a single cross entropy because you have only one output over here. Whereas in case of your machine translation and those kind of things, you had a complete sentence as an output. That's why the loss function was sum of cross entropy. And also you will learn here also, you will learn via gradient descent, and the weight of all these CNNs as well as this RNN will be updated all at once via backpropagation. Okay, here you will have backpropagation through time, here you will have normal backpropagation, here also these weights will also be learned via backpropagation. Okay. Okay, another task that you have that is sort of important is video captioning, right? Okay, so the task is you are given a video and then you have to convert this to, so you have to generate a caption for this particular video. Okay, so for example, if you, I'm not sure whether this is visible to you completely. So there is a man who is walking on the rope. So he's walking on the rope. So the caption that should be generated is a man walking on a rope. Okay, so how do we process this kind of thing? So now you have a sequential thing, right? Because in videos you have different frames, and every element of that sequence is an image. Okay, so every image would be passed via CNN, and this would be connected in an RNN kind of fashion. Okay, so this is RNN of CNN that you can see. Okay, from there you will get this representation that you will feed it into. Now output is a sentence, so your decoder module would be a RNN, right? So this is your input, right? And then you can generate the sequence. Again, you can have an option too, where you have input to sort of every time step. That also you can have. Okay. So yeah, these are not just the only examples that you can think of. So there are many more examples, many useful examples that you see in your real life. Okay. Like people are trying to, what people are trying to do, let's say you have a movie in Telugu, right? There are many good movies in Telugu that Hindi audience can't really enjoy because of the language barrier. Even when people dub those movies, those dubbings are not very great, and the facial expression are not that great, right? So what people are trying is that train a AI model or a machine learning model that can first of all change the language. So what would be the task that you will have? You will have, first of all, you will have, your input would be speech, right? From that speech you need to extract the natural language, then you have to translate it, then again convert it back to speech, right? So this is the task that you have. Okay, and also given this speech, right? Given this speech and the existing video, you have to create a new video in which your lips are synced. So if some of you are Hindi speaking people, you might have seen when you are watching some South movies or even some Hollywood movies if you are watching it in Hindi. So the person might be saying something else, but his lips are completely off the place. So these kind of things people are trying to do. And there are many more applications that people have tried to develop based on this encoder-decoder kind of module. Okay. Okay. So, any doubt or anything that you want to ask in this before we move ahead?
No, sir.
Okay, so we'll go for attention mechanism. Okay, again, I mentioned this in the beginning of the lecture also. I'm only discussing one kind of attention mechanism that was there in the course. There are other types of attention mechanism also. So the attention mechanism would just vary. Okay, I'll tell you how would these attention mechanism vary when we discuss about this type of attention mechanism. So there are some dot product based attention mechanism also. There are some you will see terms like key, value, these kind of things there. You can sort of look at these kind of things. Then these kind of attentions were like motivation for something known as transformers that are very common today. But as I have mentioned in previous lectures also, these videos were recorded at least 3-4 years back when these transformers were not that kind of at peak as it is today. So these topics were not covered at that time, but you can definitely have a look because these are the recent trends that you see. So all these chat GPTs or this new facility that these OpenAI people have proposed, that they will sort of generate videos from the text. You have this image generation from text. These kind of ideas these days are using transformers in some way or the other. Okay, there is a new trend that is also picking up is something known as diffusion models. So if some of you have some background in mathematics, you can also try looking at these kind of models just for the sake of completeness. Like if you're doing a deep learning course, you should have some idea like what are these. Okay, so these things you can see. Okay, now coming back to attention mechanism. Okay, so if you look at the machine translation task that we did, example that we did, what we did is we used the final layer of RNN of our encoder, okay, and we pass that final output to your RNN second, that is your decoder RNN. Okay, so what does this final output of your encoder represents? Okay, so final output of encoder, if you sort of try to think logically, what would it try to capture? Because the learning is from end to end, so you will learn to generate these representation in such a way that it should help you to do these kind of translation. Okay, so in the process of doing that, so what do you think your final output of your encoder should be? Okay, so what I feel it will try to do, again, this is just sort of intuition that I'm giving you. I don't have a valid proof for this, and I'm also not sure whether it is true. But what it should try to do is, it should try to sort of capture the meaning of every word, right? Right. And again, the way in which this word is used, whether this word is used as a noun or a pronoun, so that these kind of things are helpful in translation. Okay, so the context in which it is used. Okay, and all these information are stored in this particular vector. Okay, so this is one thing. So when we do translation, let's say there is a sentence, मैं घर जा रहा हूँ. When I'm trying to find the like the output I, the I is only dependent on मैं. Okay, so it is not much dependent on the other words. Obviously, it will depend on the complete sentence for the context, but it is more dependent on the word मैं. Okay, so if we have some mechanism via which we can sort of use all these vectors, okay, and we take a weighted combination of all these vectors and pass it here. Okay, so let's say this is alpha 1 1, alpha 2 2, alpha, okay, sorry, this should be alpha 1 2, alpha 1 2, alpha 1 3. So we want a different kind of weighted combination for first input, we want a different kind of weighted combination for second input, and so on. Okay, so if we have such a mechanism, we can hope that we should do better on at least these kind of tasks, such as your machine translation and those kind of things, those kind of a task. Also, one more drawback that I feel the earlier mechanism have is, because as I said, this uh, representation of the last output will try to capture many information about the complete sentence, there can be an information overload over here. Okay, there can be a information overload here, so that you are not able to bifurcate all the information very clearly. Okay, but in case of mechanism, because your every input to your decoder is sort of a weighted combination of all these HIs, you can expect that it would perform better in case of this, because of this like a lot of information can be passed via this weighted kind of a sum at different levels. Okay, so how do we sort of achieve these kind of thing, that we want different weights for this kind of a thing? So we model this via something that is known as attention mechanism. So this is one attention mechanism. Okay, so what we will do is, we will try to define these weights. Okay, so this is your alpha 1 3 over here represents what is the connection, or the, so okay, so this is the weight that you want to assign to time step 1 of your encoder going to the time step 3 of your decoder. Okay, so what are the things that this should depend on actually? Okay, so let's say if this is going from time step 1 of the encoder, then it should definitely depend on this particular vector, right? So this should depend on h1, right? And where it is going? It is going to time step 3, right? So it should also depend on this particular thing that you have obtained till this point. Okay, so it should depend on st. Okay, so we have these two things. So why don't we take a sort of weighted combination of these? Not weighted, but sort of a parametric combination of both of these. For that, we have u attention. So these are my parameters, hj plus w attention st. Now again, this hj is d cross 1. So what is the possible dimension for this u attention? So this can be some d1 cross d, and this w attention can also be some d1 cross d. Okay, so this combination, this sum that you will obtain would be some d1 cross 1. Then we apply this tan h operation on top of it. Okay, now after tan, so this tan h operation on a vector would be component wise. Okay, so if you have 1 2 3 that you have obtained using this sum, then tan h of this would be component wise. This would be tan h1, tan h2, tan h3, right? And this is the vector that you will obtain. But we wanted a weight over here. Rather than a vector, we wanted a weight over here. So obtain a scalar out of this vector, we can again multiply it via sort of a row vector. Okay. So to represent this row vector, we have this V transpose of attention. So this V would be your D1 cross 1. So that when you have this transpose, then it becomes 1 cross D1 cross 1, and your output is 1 cross 1. Okay. So this is the way you can obtain your weights. Here the learnable parameters are what all are the parameters that are there to learn. So U attention, W attention, and V attention. These are the three parameters that you have to learn. Okay. Now you have sort of obtained these weights. Let's call them EJT right now. What we want to do is we want to sort of scale them between 0 to 1. So whatever values they have, we want to scale them between 0 to 1. To do so, we apply softmax layer to obtain alpha JT. Okay. Now alpha JT is your final weight to your attention. Okay. So what is the input that you would be passing on to your RNN? So you would be passing on this weighted combination, that is alpha JT into HJ. This is your H1, H2. So this is alpha 13 H1 plus alpha 23 H2. This is the weighted combination that you would be passing to this particular layer, this particular time step, not layer. Sorry. Okay. So your RNN would look something like, what would be the inputs to the RNN? First would be the ST minus 1 that it is obtaining. Second would be the last output that it has produced. And third would be this attention kind of thing that it would obtain. And the last two are concatenated with each other. Okay. Any doubt in this attention mechanism? If you have, you guys can please ask. Like this is the attention mechanism, how this would work. Again, these weights would be learned during backpropagation and those kind of things. Because all these functions are again smooth. Your tan h is smooth, right? You can differentiate and you can backpropagate using gradient descent. Okay. Okay. If no doubt, then I'll move to attention over images. Okay. So if you have, let's say, a sentence, what we saw is that at different time steps, we had different vectors that we were interested in, right? So that's why we had different weighted sum over here. Okay. Now, what is the motivation for having attention on images? Okay. Let's say your task is to identify whether you have humans or not. Okay. Or maybe the kind of task that we had, image captioning. Okay. So in that kind of task, right? So in case of image captioning, the caption that we obtained was a man playing frisbee. Right. So for word man, there would be a certain patch of your image. Let's say this is the patch of image. This is the patch of image that is responsible for the word man to be produced. Okay. And again, you have a patch of image that is responsible for frisbee. Okay. So you want to have sort of uh, weighted kind of a sum of these positions so that you are able to focus on the right part. Okay. Now, what we can do is, let's say you have some convolutional neural network, that is your CNN. For this convolution, okay, like if you reach to the layer of your fully connected layer, okay, then attention don't make a lot of sense. Okay. So what we do is, in this convolution layer, you have 512 channels of 14 cross 14, right? So we treat all these spatial 14 cross 14 elements. So there are 196 sort of these kind of vectors of length 512. We treat these as your spatial representation, and we apply attention on these. Okay, so you don't apply your attention on channels. You apply this on, let's say this is of size 14 cross 14. Okay, so you will have 196 such vectors of length 512, where 512 is your channels. Okay, and then you will apply attention on top of it. Okay, now what is the intuition behind this is, okay, you try to imagine how does your sort of uh, CNN work. Okay, so let's say this, if this was 224 cross 224, at this, okay, I think, okay, let's say this is your image. When you sort of started from here, you will look at a window around it. Okay, so this point over here not only represents a particular pixel in the image, okay, but what does this represent? This represents the quality of this particular portion in the image. Okay, then again you will slide, you will sort of represent this particular thing. You will sort of start keep on representing different portion of the image. Now when you do sort of some max spool, what happens is, this max spool, this particular element now not only represents this section, but represents a larger portion of this image, right? And again sliding, because this is sort of a sliding thing, so you can have different such portions. Okay, so if you are taking one channel in this CNN over here, what you are trying to capture over here is some portion of the image that or the some features of the image that your CNN has intrinsically learned. Okay, so this is one feature of your image, right, that your CNN has learned. This is another feature of your image that your CNN has learned, and you're trying to do an attention over all these features. Okay, this is the idea behind your attention over images. Any doubt in this? Okay, so for today there is this last thing left, then we'll move on to some questions that I have added. Okay, so this is known as hierarchical attention. Okay, so let's motivate this by the same example that was done in the course. Okay, so let's say you are trying to develop a chatbot. Okay, so the response of a chatbot, like you might have encountered many chatbots. What they do is they reply just based on the last response that you have sent, right? They don't care about whatever we were talking about earlier, but it will respond only on the last message that you have sent. Okay, but we don't find these kind of chatbot very effective. Okay, these are not very efficient kind of chatbots. Okay, so what are the good qualities of a chatbot? That what it should do is, it should keep in mind whatever conversation is going on, and based on it, it should reply, right? So for example, over here, some user asks that, can you suggest me a good movie? So bot says, yes, sure. How about Logan? So Logan is the movie that suggested. So user asks, okay, who is the lead actor? Now, if you just look at this sentence, who is the lead actor, if you don't care about the background, okay, so this doesn't make any sense. Like, who is the lead actor where? So your bot would get confused and won't be able to answer. But if it has sort of remembered these kind of things, then it will look back and say, okay, this is about the movie Logan. Then it's a Hugh Jackman, of course. Okay. So this is the kind of thing that we are trying to capture. So now, what is a sequence? Oh, sorry. What is a sentence? I meant. What is a sentence? Sentence is a sequence of words. Now the case that we are trying to tackle over here is, that is sequence, that is sequence of sentences. Okay. So to model one sentence, we have this RNN, right? To model this sentence, we again have this RNN. To model this sentence, we again have this RNN. Again, one small thing, the weights over here would remain same. This is U, this W, but we want the output of every sentence. Okay. So let's say you have a document of 1000 sentence, and whatever task you want to do based on this 1000 sentence, you just pick the last vector after, let's say if every sentence carried 10 words, so 10,000 words, right? So if you just pick up the vector after reading 10,000 words and you pass it to the decoder, then sort of imagine the amount of information that you are trying to sort of squeeze in this small vector, and how well your decoder would be able to do. Okay. So this is another motivation for sort of doing this sequential manner, that after every sentence you are finding a representation for that sentence and you are separating it out. Okay. And that you are again processing as an RNN, because you have different representation for different sentences, and you don't know the how many sentences that you have and those kind of things. And now this you are passing to your decoder. Okay. So because we are sort of just like extracting the representation for different sentence, we can maintain this weights, right? Otherwise it would become very difficult for you, right? That you will have different weight for first sentence, different weight for second sentence. Now how many weights you want to store and those kind of things. So what you will do is, you will have same weights, but you will have different outlets from here. Okay. So this is the first RN for sort of my first sentence. This is for second sentence. This is for third sentence, right? Now you again sort of treat this as an RNN. This is your first, this is your W, this is again your W sum, and this final output you will pass to your decoder layer. Okay. So now this is a normal hierarchical hierarchical encoder-decoder model. Now how do we sort of do attention in this kind of things? We'll look via another example. So example is, you have a large document. Okay. You want to summarize, like whether this, let's say you have some news article. You want to sort of categorize it, whether this news article is related to politics, sports, finance, and those kind of things. Okay. So in your article, you will have different sentences that again you will model as this thing, right? And those sentences combined would be passed on to a sort of feed forward neural network that will classify the type. Okay. Now if you want to incorporate attention on top of it, what you can do is, so rather than just passing the final layer, what you will do is, you will have a this kind of attention mechanism over here, right? This attention mechanism is a common attention mechanism for all of them. So the weights that you will learn, U attention, V attention, and whatever the rest you have, that would remain same for all these three, but there would be attention mechanism over here. Now because you have three different sort of, there is an RNN at the second level hierarchy that is running, so you will again have one more attention here. Okay. So rather than just passing this final layer, what you will do is, you will pass a weighted sort of sum of these three. Okay. And this is what is represented by this image over here. Okay. So this is your input word W2, W1. You have one hierarchy at this level. This is your word encoder. So you have attention over here. Now you have obtained your, this is your sentence representation. You have different sentences. Now again you have a second level of attention. And finally you have some softmax if you are doing some classification. Okay. This is just a mathematical way of writing it, that you have some. So what is this Okay, so sorry. So if let's say this thing is represented by hij, right? Sorry, yeah, this is hij, and these are your SIs. Okay, so the lower level are your HIs, these are your SI. So what is the input to your first RN? First RNN are your words, right? And the previous sort of this, right? So for every layer, this is your previous input plus the current word. This you will pass by RNN to obtain your current hij, right? Then you will obtain the corresponding weights over here, and using those weights, you will obtain your SIs. Now for second level of RNN, your output depends on HI minus 1 and SI, right? There is sort of, yeah, okay. So this was hij, this is hi. Just remember this h over here is not same as this h. Okay. Then again you will have some weights, and the final output you can have a weighted sum of these things. Okay. So this is how your hierarchical attention works. Any doubt in this? Okay. We have some questions that are there on that are related to this year's assignment and are from previous year's assignment. We'll try to look at them. Okay. So first question is, if we make a vocabulary of an encoder-decoder module using the given sentence, what will be the size of our vocabulary? Okay. So the sentence that is given over here is, encoder-decoder models are very useful. Okay. So what do you guys think? What is the size of vocabulary that we'll have? You can
So
type in.
6.
Okay, somebody says 6. What other people think? Okay, so just we can scroll up a bit. Okay, so in RNN, one thing that you should sort of keep in mind is you should know when to start and when to stop. Okay, so when you create your vocabulary for RNN, so here, if you look, there are 6 unique words: 1, 2, 3, 4, 5, 3, 4, 5, 6. There are 6 unique words, but you should also train your model to predict stop, and you should also have the word start or go in your vocabulary. So 6 plus these two, so there would be 8 unique words in the, so the size of vocabulary would be 8. So if you have a similar question in this year's assignment, you can answer accordingly. Okay, so you should include your stop and go in the vocabulary. Okay. Okay, so okay, this is the second question. So the question is, we are performing the task of machine translation. So the task is machine translation. So what is your input? Input is some sentence. Output is also some sentence. Using an encoder-decoder module, choose the equation representing the encoder module. Can you guys please answer?
So A option.
A option is CNN.
Yes, sir.
So like your input is, so okay. So the question is the equation representing encoder module, right? So encoder module deals with your input. First thing is this. So what is your input? Input is your sentence. So what is the kind of model that deals with your sentences? So CNN deals with your images, right? So the kind of architecture that would deal with the sentences are RNNs. Okay. And in encoder, okay, so if you look at, I'll just scroll up a bit. For example, if you have this, okay, so you have different words that you have as an input, and you will have this earlier states that is coming. So what should be the input to your RNN? So input to your RNN should be HT minus 1 and XIT at that particular step, right? This option is not correct because this particular thing represents whatever output you have obtained in the previous step, you use that as an input. But when you have machine translation, your initial sentence is already given to you, right? So that's why we are picking this option. So A is not correct, whoever answered, because CNN deals with images, not with your sentences. Okay. Okay. So there is a similar question. I expect you guys to please like at least type it in the chat box after reading the question, whatever option you think is correct. Okay, so the task here is given below are some tasks to be performed using encoder-decoder module. Select the task for which RNN of the CNN model should be suitable. RNN of the CNN should be used as an encoder. So you have something, you do some CNN kind of a thing on this, and then you obtain something, you pass it here, you have something, again you do CNN kind of thing. Somebody says image captioning, okay. So, okay, somebody has said image captioning. What other things, please, can you answer? Okay, so we did this example, right, few moments ago, where we had RNN of CNN, I wrote also there. So what do we mean by RNN of CNN over here is that you have a sequence of elements on which you are applying CNN. So on what things you apply CNNs? You apply CNNs on images. So you have sequence of images that you want to process as your input. So in what kind of task will you have sequence of images as your input?
Video.
The correct answer is video caption. Okay. Okay. So I think this question you guys can answer. We are given a task where we have to take as input some sequence of sentences. Okay, now we have sequence of sentences. So this is sequence of sequence. And produce a sentences on as an output. Which of the following model will work best for this task? Okay. What do you guys think? We have sequence of sequence. Yeah. Somebody said A. A is correct. We will have hierarchical encoder-decoder network because we have sequence of sequences. Okay. Okay. So again, so we are using hierarchical encoder-decoder network for document summarization. What is the number of levels at which we need to implement attention mechanism? So as we saw in the like the case that we had, so when you are having a document summarization task, so there is first sequence is formed out of words, and this is called your sentence, and the second sequence is formed out of sentences, that is your documents. So there is two level of hierarchy, right? So 2 is the correct answer. Okay. Okay. So let's look at this question. We implement an attention mechanism for images for the output of one of the CNN layers. Which layer's output should we use to implement our attention mechanism? So it is asking like if you have a CNN, what layer of CNN should you pick to apply attention on? Okay. So as I said, we don't want to use fully connected layer. We don't want to use max pooling layer, but we want to use the CNN layer which has spatial information. Okay. This is what we discussed. Okay. So this question is pretty easy. So which of the following output function is most commonly used in decoder as the encoder-decoder model for translation task? So when you have model for translation task, so your decoder is an RNN, right? And what is the most common output function used for RNNs? Softmax, right? For RNNs you use softmax, because of which you suffer from this vanishing gradient problem, right, that we discussed in last class. Okay, so this is what I had prepared for today.